Hello, everyone. Welcome to today's Docker education session. I'm thrilled to have you join me as we explore the fascinating world of Docker. As we all know, in the realm of modern software development, Docker has emerged as a pivotal tool, reshaping the way we conceive, develop, and deploy applications. Its significance cannot be overstated, as it has become an integral part of every developer's toolkit. Did you know that during the first year of its release in 2014, Docker recorded more than 100 million downloads? And today, almost 95% of companies use Docker. Throughout this session, we'll embark on a comprehensive journey through Docker, covering everything from fundamental concepts to advanced techniques. By the end of our session, you'll have a solid grasp of Docker's capabilities, networking, Docker files, Docker commands, Docker Swarm, and how to leverage them effectively in your projects. At its core, Docker is a platform that enables developers to package, distribute, and run applications in isolated environments called containers. Docker emerged as a cornerstone of modern software development due to its transformative impact on the entire software lifecycle. Firstly, it addresses the age-old challenge of software portability by encapsulating applications and their dependencies into self-contained units known as containers. These containers are lightweight, portable, and agnostic to the underlying infrastructure, enabling seamless migration across different environments from development to production. This portability eliminates the notorious "it works on my machine" problem, ensuring consistency across diverse environments and minimizing deployment friction. Secondly, Docker leverages containerization technology, which provides a level of isolation akin to virtualization but with significantly lower overhead. Unlike traditional virtual machines, containers share the host system's kernel and utilize resources more efficiently, resulting in faster startup times, reduced memory footprint, and higher scalability. This efficiency makes Docker particularly well-suited for microservices architectures, where applications are decomposed into smaller, independently deployable components. Docker also fosters a culture of collaboration and reproducibility by enabling developers to package their applications and share them through Docker images. These images serve as immutable blueprints for creating containers, ensuring consistent environments across development, testing, and production. Furthermore, Docker Hub, a public repository of Docker images, facilitates the sharing and discovery of pre-built images, accelerating development workflows and promoting code reuse. Additionally, Docker aligns seamlessly with modern DevOps practices, enabling organizations to embrace continuous integration, continuous delivery, CI/CD, and infrastructure as code, IAC principles. With Docker, developers can define their application infrastructure using code, infrastructure as code, version control their Docker files alongside application code, and automate the entire deployment pipeline. This automation streamlines development workflows, increases deployment frequency, and enhances overall software quality. Docker differs from traditional virtualization methods primarily in its approach to resource utilization and isolation. Unlike traditional virtualization, which involves running multiple virtual machines, VMs, each with its own operating system, OS, on a hypervisor, Docker employs a lightweight form of virtualization called containerization. In traditional virtualization, VMs are heavyweight constructs that require a significant amount of system resources, including CPU, memory, and disk space, to run. Each VM runs a complete OS, which includes a kernel, libraries, and system binaries, leading to duplication of resources and increased overhead. In contrast, Docker containers share the host system's kernel and only package the application and its dependencies, along with any necessary runtime libraries, into a lightweight, portable unit. This approach eliminates the need for multiple OS instances, resulting in a smaller footprint and more efficient resource utilization. Furthermore, Docker containers provide a higher level of isolation compared to traditional virtualization methods. While VMs offer strong isolation by running separate OS instances, Docker containers leverage features of the Linux kernel, such as namespaces and control groups, C groups, to provide lightweight, process-level isolation. This isolation ensures that containers remain isolated from one another while sharing the same underlying infrastructure, allowing for more efficient resource utilization and faster startup times. Additionally, Docker containers offer greater flexibility and agility compared to VMs. Since containers share the host OS kernel, they can start and stop more quickly, enabling rapid scaling and deployment of applications. Containers also promote consistency across environments, from development to production, by encapsulating the application and its dependencies in a portable format that can run anywhere Docker is installed. Overall, Docker's lightweight containerization approach provides a more efficient, agile, and scalable alternative to traditional virtualization methods, making it particularly well-suited for modern software development and deployment workflows. Understanding these distinctions is crucial for leveraging Docker's unique advantages and maximizing its benefits in various use cases. To become proficient in Docker, mastering its commands is essential. While numerous Docker commands exist, I'll focus on just 10 crucial ones for this video. Let's start with Docker run, the cornerstone of Docker commands. This command breathes life into Docker containers. It's straightforward. You specify an image to run, and Docker does the rest. Need a web server? Just Docker run it. Testing a new database? Docker run has you covered. Next up is Docker build. This command empowers you to craft custom Docker images. Using a Docker file, you define the blueprint for your containerized applications. Once your Docker file masterpiece is ready, a simple Docker build command brings it to life, creating a deployable image. Now let's dive into Docker pull. Consider it your gateway to a vast array of Docker images on the internet. Need a specific PostgreSQL version? Docker pull, Postgres. With Docker pull, fetching Docker images from registries like Docker Hub is a breeze. We also have Docker push. Once you've crafted your custom Docker images, it's time to share them with the world. Enter Docker push. With a simple command, you can upload your images to a Docker registry, making them accessible to your team or the entire Docker community. I use Docker exec a lot as well. This command grants you backstage access to running commands inside Docker containers. Need to troubleshoot a misbehaving container? Simply Docker exec into it and start diagnosing. Want to perform maintenance tasks on a service? Docker exec enables real-time interaction with your containers, a crucial tool in your Docker toolkit. Also, Docker PS is also a commonly used command. It provides a snapshot of running containers. It gives you valuable insight into which containers are currently active, their status, and basic information like their names and IDs. Then there's Docker PSA, which extends the view to include all containers, not just the running ones. This command is handy for getting a comprehensive overview of both active and stopped containers, along with additional details such as when they were created and their exit status. Next up is Docker logs, a command used to view the logs generated by a specific container. Whether you're troubleshooting issues or monitoring container activity, Docker logs lets you access valuable information such as application output, error messages, and system events directly from the container. Finally, we have Docker images, which provides a list of all locally available Docker images on your system. It includes both official images pulled from registries like Docker Hub and custom images you've built using Docker build. This command is essential for managing your image repository, allowing you to view, delete, or tag images as needed. When it comes to Docker, Docker files are the backbone of containerized applications. These files contain a series of instructions, akin to a recipe, guiding Docker on how to build container images automatically. Understanding Docker files and mastering their creation is crucial for anyone venturing into the realm of containerization. To start, let's discuss the anatomy of a Docker file. Each Docker file typically begins with a from instruction, which specifies the base image upon which your container will be built. This base image serves as the foundation for your application environment. For instance, if you're working with a Python application, you might initiate your Docker file with from Python 3.9. Next, you'd often set the working directory inside the container where your application code will reside. This is accomplished with the workdir instruction. It ensures that subsequent instructions are executed from within this directory. Workdir/app/app. Now comes the pivotal step, copying your application files into the container. Docker provides the copy or ADD instructions for this purpose. These commands facilitate the inclusion of your application code into the image. Copy/app